Buenas tardes! July 13th, 2019. Our subject today is cubics with matrices for undergraduated people. Well, everything began with a polynomial of degree n of x equals to 0 and Rn roots. This is our set R. We take it by the characteristic polynomial of an ordinary differential equation. We did it for n equals to 2. Now we're going to n equals to 3. Everything began generally taking the exponential of Tm, where m is the companion matrix of the polynomial. By one side we have the exponential of RIT times constant. The other side of the equality we have f1 of t, f2 of t times constants. And we know those constants are a T matrix, linear dependency. And we got a quantity, uncountable quantity of equations for any t in R, exponential of xt plus polynomial of degree n minus 1 of tx equals to 0. This respects our set of roots for all t in R, and there appears another complex roots. As we saw, exponential of z equals to z leads to infinitely many solutions for branches of the logarithm. And taking exponential of rt, the Taylor series, r power 2a over a factorial times t power 2a. For each a in n, we have a countable quantity of equations, x power 2a plus polynomial degree n minus 1 of xn equals to 0. Again, this preserves R, but has degree a. It has more roots than n. Okay, now let's search our next section. From exponential to cubic, we know how to go from the third degree to the exponential. But when trying to take down the exponential to the third degree, let exponential of t equals to d. T is the logarithm of d, natural logarithm. f1 of logarithm of d equals to a. f2 ln d equals to b. f3 over 2 equals to c. And we try to revert this system, but we did not find S key p to know who is the sum, who is the product, who is the second sum. The sum of 2, the product 2 by 2 is q. We need to know R1, R2, and R3. This is not interesting. But without knowing the roots and with two equations, we got a solution. All we need is beta equals to alpha 2, y equals to alpha power 2x. Okay, we have t equals to u, t equals to v. U is alpha power 2x and v is beta. Exponential of v is beta, exponential of u is alpha. So if by one side we have a0, a1x, a2, x2, and the other side b0, b1x, b2 of x2, we can drop the x2 multiplying the first by b2 subtracting a2 times the second, b2 times the second, the first, minus a2 times the second. Okay, now translating alpha power to x, y, beta power to x, y2. Rearranging, here is the L1x plus L0. We have to do it again with a third number w, exponential of xw, c0, c1x, c2, x2. So now the degree is 3. We need 3 informations to solve the system. Repeating the algorithm above, c2 times the first minus a2 times the second or the third, gamma equals to alpha 3. We have c2y minus a2 y3 equals to L1x line plus L0 line. Now we combine both. Who is minus x? This guy divided by L1 and this guy divided by L1 line. So we have function of y and y2. Here is y and y2, and function of y and y3, and here is c2y a2 y3. The x goes away and we got an equation in y. Who is y? The exponential of alpha x is equal to the logarithm of y at the basis alpha. This is our desired cubic equation. A1 y3 plus a2 y2 plus a3 y plus ad equals to 0. Our family of cubic equations is F3. Here is polynomial of degree n, exponential equals to Bhaskara, and polynomial of exponential of xt multiplied by 1 minus s1 plus s2 of t minus p of t, where these functions of t are known. What happens when I try to solve second degree Lambert? It's unsolvable. By this general relativity and quantum mechanics towards the generalization of the Lambert W function, the guy studied big O approximations. And here is the conclusion. If the function, the right hand side is the first degree, the solution is known. Now the actor wants to solve the equation of degree 2. He creates an independent variable y for such decomposition. Exponential of minus rxy equals to a0, x minus r1, and the exponential of minus rx2 minus y equals to b0, x minus r2. Now we're going to solve x as a function of y using the first equation. X is w of z1, x is w of z2, where z1 is a function of a0 and z2 is a function of b0. and the two x's are equal. We have a dependency in y. W equals to W, R1 minus R2 is equal to this object. And who is x? Exponential of minus 2xr is known. By this equation, we know 1 over 2r's logarithm of w times w divided by function of y. Well, here are two properties he wants to use, but we did not use. This simplifies something, but it's not general. We lose generality. I tried to solve it by myself. What I got? Nothing. The case where R1 is equal to R2 is equal to R is known. Our alpha, the difference is 0. The exponential of xr, we divide the exponential by 2, appears the square root of a0, b0 x minus r. Who is x? Is w of something plus rr over r, is w of plus or minus lambda, is key over r plus r, it's 1 over 2r w1 plus w2 plus 2r big R. So we have equality of fractions, and w2 is equal to w1 times a fraction. So the w of plus or minus lambda is 1/2. w1 fraction equals to w1 over y. Okay, this is simplified. We have minus 1 plus 1, 2 over 2. Who is y1? Is a constant times y. Who is the constant? W of minus lambda. So constant y, exponential of constant y, is z1 because the w function applied to z1. Who is z1? We know the formula of z1. Now a0 multiplied by key exponential of key y, exponential of ry equals to r. Where is y? Let me see. Y one side, y the other side cancel. A0 key gamma power to y equals to r, where our gamma is the exponential of key plus r big R. Now we isolate y. Logarithm on the basis gamma of r divided by a0 key, which is equal to logarithm above minus logarithm down divided by logarithm of gamma. This is for alpha equals to 0. What happens when alpha is greater than 0? We go into nowhere. Here appears alpha. The same way appears alpha here and here. We know x is 1 over 2r, but y depends on alpha, so alpha is not cancelled. W1 is appeared, x is minus alpha, W2 with alpha, Z2 is W exponential of W, and here is the monster. The equation is B0 x minus r plus alpha exponential of r x2 minus y equals to 1. So, who is xr2 minus a? The exponent. Logarithm above minus logarithm down. Who is xry? Here it comes, multiplying or adding to xr. Logarithm of 1 is 0. The signal is exchanging, and we know that y is a function of x. All we got is that. We don't have how to eliminate the dependency. So here is another try. Exponential of minus cx is a times quadratic. S is 0. Ys is 0. We can complete the square. So x2 minus p is w, is double or u function of some z. So x is plus or minus the square root of w minus p, isolating x. So the exponential of minus or plus c square root is equal to aw. Okay, here is exponential of minus cx. So, who is the exponential? Exponent is the logarithm of aw, logarithm of a plus logarithm of w. Who is w? Exponential of w is z. Who is logarithm of w plus w, logarithm of z? We take this and substitute. C2 w minus p is equal to ln of a plus ln of z minus w squared. And now, what we're gonna do, we solve for w. So we have w squared, w times a constant, and c2p, c2w is there, and we solve by Bhaskara. W is a function. Minus b plus or minus the square root of delta over 2, 1. So all we know is that there is an equation 2 worse. We have w exponential of w equals to z is a function of z. Function of z exponential of function of z equals to z. So let's go to something better. Hungerford says the cubic is solvable by radicals. We have already done second degree, and now we're going to third degree. By the companion matrix 0, 0, 0, 1, 0, 0, 0, 1, and minus p, q, minus s in the third line, we can go on to a equals to 4, a equals to 5. We can reduce x5 equals to minus 4x2 plus 30x plus 2 to x3, solving this guy. Coefficient of x2 is equal to minus 4, function of kps equals to 30, function of pks equals to 2. There are several solutions. We have this equation. Who is the exponential of ntm? f1 of nt, f2 of nt, f3 of nt. This is the exponential of mt powered to n. So we have another matrix f1 of t, f2 of 3, f3 of t powered to n. The nth power is the nth factor of t. Solved exercise. We see easily an expression of exponential of tm by means of r1, r2, r3. So here is the exponential of tm is our matrix E multiplied our t inverted and transposed. With Cardano, write down an expression for exponential of tm by means of s, q, and p. So we have to use Cardano. R1 is the sum of square root of z1 plus square root of z2, and this z1 and z2 is a function of the cubic coefficients. Okay, let's see what happens with matrices. First, if S is a number, Q1 is a number, P is a number, and M is 3 by 3, the companion matrix is the solution of this cubic times identity equals to 0. We have that property, the power and nth power of M. The lines grow. First line M1, second line M2, third line M3, fourth line M4. So M2 is power 2, power 3, power 4. We can get M for calculating M2. We have M1 row shifted up, the second line to the first line, the third line for the second line, and all we need to is to calculate the third line. Okay? So the same companion matrix M is the solution of exponential of Tm is equal to f1 of t plus f2 of Tm plus ft of 3 over 2 times M2. Here I define delta. When defining logarithm of identity, we have logarithm of 2kpi is equal to 1. The exponential of 2pqi is 1. Logarithm of 1 is the set of exponential of 2zpi. In matrix Jordan form, 0 and minus 2kp, 2kp 0 is the Jordan block, representing a complex number. Its block must be or first and second columns or second and third columns, and the third eigenvalue must be 0. Why? Because we are solving exponential of m equals to identity. The exponential of 0 is the identity. The exponential of this complex number is 1. So all the logarithms of the identity are a sum over a subset of z of PDP minus 1, where our diagonals are deltas, our p's have determinant different than 0. So we can sum one d key of this type to one d key of the second type, and identity times identity will be identity. This sum is at most for every key in Z, so it's a countable sum. So this difficulty appears when trying to define the exponential of m equals to t if and only if m is the logarithm of l logarithm of t plus l. Because t power 2m is the exponential of a product where m is on the left or m is on the right. So we have a difficulty to extending this to f1 big F multiplying by m on the left or on the right, multiplied by square on the left or on the right. This is not solved. So we're not going to non-commutative algebra. We're going to the commutator. Suppose Sx equals to xs. Suppose uv equals to vu. Suppose yq2 equals to ky. And go ahead. Let's use Cardano to solve t3 minus s t2 plus q1 t minus p1 equals to 0. These are n by n matrices. We exchange t by x plus 1/3 of s to eliminate the minus s2 factor. We get 0 is equal to x3 plus p2x plus pq2, where p2 is a formula and q2 is a formula. Now we're going to solve this simplified equation. X is the sum of u and v. We need to know u and v. u3 and v3 reduces to y, a square quadratic equation, y2 plus q2y minus constant equals to 0. So if x is u plus v, who is x3? u3 plus 3uv, u plus v plus v3. Who is p2x? p2u plus v. Who is q2? The same q2. So we search for a solution of this system. u3 plus v3 plus q2 is 0, and 3uv plus p2 is 0. We let y be minus 1 over 2 q2 plus y w0 d0 w0 inverted. This is the solution of the quadratic. Our delta is the square of a matrix. w0 d2 0 w0 inverted. So this is the square root of delta, and there are n solutions of the quadratic, yn. We're going to extract the cubic roots of yn. Each yn has cubic roots, z and key. The same Jordan diagonalization. Now you evaluate pairs of z such that z1i times z1j is equal to minus 1/3 of p2. This can be done by computer. So evaluate x from z's and evaluate t from x. You have solved the Cardano equation for matrices. Now, example of classifications. We have three roots, or they are all distinct, or they are all equal, or they are repeated, two repeated and one not repeated, or they are two complexes and one real. We have 3 or 4 cases. First case, suppose R1 is minus 2, R2 is minus 3, R3 is minus 4. So we have our equations: exponential of minus 2t for all t, exponential of minus 3t for all t, minus 4t for all t. Okay, who is f1 of t? 6 exponential of minus 2t, f2 of t. 5 over 2 exponential of minus 4t, f3 of t. 1 minus 2, 1 exponentials. How we do know that? By the exponential of the companion matrix. We know who is the matrix from the exponentials. We invert the matrix: 1 minus 3, 9 over 2, 6 minus 8 over 3. Let t equals to 1. The exponential of x is f1 of 1. Okay. Generally, the exponential of x is a quadratic. See link above. Let's see the link above. L. Is a transformation which leads to minus 2, minus 3, and minus 4. But this is an exponential times summed to a quadratic. Okay. See link above. Who is A? A is f3 of 1 over 2. B is f2 of 1. And C is f1 of 1. Diagonalization this companion matrix, we have minus 2, minus 3, minus 4 in the diagonal. The 3 eigenvectors on the left and the V inverted on the right. We do the calculations for x4, do the calculations for x5. This is an example. Now, second case. The 3 roots are minus 2. X plus 2 squared power to 3 equals to 0. So we have a single equation. We have an ordinary equation which leads to C2t, C3 exponential of minus 2t by reduction of order. And we need to know C1, C2, C3 for F1, F2, and F3. When F1, 1, 0, 0, degree 0, 1 minus 2, 4 over 2, for exponential of minus 2 is Taylor expansion. 0, 1 minus 2 is the expansion of t times minus 2t. and T2, 0, 0, 1, we have C1 equals to 1. If C1 is 1, C2 is 2. And if this is 1 and this is 2, then C3 is 2. So F1 is 1, 2, 2 multiplied by the exponentials above. The same reasoning for the coefficients are the same on the left, and on the right 0, 0, 1, because we want to know F1 above and F2 on the middle and F3 on the right. So here comes 1/2 isolated. F3 is 1/2 T2 exponential of minus 2t. This minus 2 is R. Generally, it has a way to isolate and solve the equation. Divide by T2, take the logarithm, divide by T, and the equation is solved. But who wants to solve particular equations? Here is the matrix of repeated eigenvalues. Here is the matrix of eigenvectors. Here is the inverted matrix. And here is the example, the calculations for x4 and x5. Now, the third case, we have minus 2, minus 2, minus 3. One repeated and one different. We have two equations, exponential of minus 2t, exponential of minus t3. One equation with appears two exponentials and one reduction of order term, c2t, exponential of minus 2t. The same reasoning. 1 minus 2, 4 over 2, 1 minus 3, nine over 2. Where is the 9 over 2 here? So this is wrong, okay? So the C the C3 is 1 minus C1, the C2 is 3 minus C1. Here comes 9 halves. So by one side we have 6 and 9 halves. 6, 12, 9, 21 halves. And here let me see. I'm not going to solve this. So there is a algorithm to solve 1 0 0 0 1 0 1 1 0 0 1 over 2, but here appears 9 over 2, and we know who is f3 of t. So here is the diagonalization. B1b repeated, C on the diagonal. Here are the eigenvectors of B and C. The matrix inverted on the singular case, minus 12, minus 16, minus 7. Here is x4, here is x5, and this is the example. Now the next case, conjugate complex roots, the cubic roots of 2. One is this cubic root of 2 real, and the other two are b times a unitary and b times unitary conjugated. Cosine on the real part and sin on the imaginary part. So we have three equations. Exponential of c plus d it, ta-da-da, exponential of c minus d it, ta-da-da, exponential of bt, ta-da-da. So we need to expand c plus di. Exponential of ct cosine of dt plus I exponential of ct sin of dt. So c above, d below. C plus di squared leads to c2 minus d2 above and imaginary 2cd over 2 below. This is valid for plus or minus dt. And we have another matrix T line times f is the exponential of ct cosine of dt, exponential sin, exponential. And here is the example of diagonalization. C minus d, dc is a complex pair, and b is real eigenvalue. So three eigenvectors and inverted matrix, and simply x4 is to x, x5 is to x2. The exercise is to isolate the fi's from the sines and cosines. I did not invert this T line. The multiplicity is 1. When the multiplicity is greater than 1, the equation can be solved by the derivative. Okay, I think there is nothing else to say. All we have now is 4th degree, 5th degree, and higher. What we want to show? We want to show that we have a single equation, and given the coefficients of any input polynomial and without the roots, we can know the coefficients of x minus q of r1, x minus q of rn. The preceding theorem is valid for any q of x, which is an at almost everywhere analytical function, and particularly the roots might be 1, 2, 3, and n. We have the algorithm for solving the quintic by hypergeometric n plus 1 fn of something. So we have to solve 4th degree equations. And this can be generalized to n, where n is greater than 5. The 5th degree is theta genus 1, the 6th degree is theta 2, and the nth degree is theta n minus 4. Out of charity, there is no salvation at all.